Suppose you just got back to the lab after the pandemic-induced lockdown. You saw an unknown sample left unlabeled by your lab mate, and all you can see is that it is in powdered form and blue in color. You got curious about how it looked like on the nanoscale and wanted to use an SEM. Scanning electron microscopy requires at least three things. It requires a specimen of your sample, obviously. It also needs an electron source. This electron source bombards your sample with incident electrons and displaces the low-energy electrons in your sample. Finally, it needs a vacuum environment. This allows the electrons to move freely inside the equipment. Now that we already know the basics, let's add a few more. A cathode serves as the equipment's electron source. And then we have the anode. The high electric field between the cathode and the anode speeds up the flow of electrons, making them reach your unknown sample faster. But these components alone leave your sample bombarded with an extra wide diverging beam of electrons, which is unfortunately not that useful in this case. This is why we need a set of electromagnetic lenses. These lenses help create an electron beam narrow enough to only pierce into the intended portion of the sample. For discussion purposes, let's say this is how your sample looks like from the top view. Scanning coils allow the incident electrons to scan your sample in a rasterized pattern, which is, in layman's term, from left to right, top to bottom. The cathode bombards these closely spaced points with incident electrons over an equal amount of time and displaces the low-energy electrons in your sample. These displaced electrons are called secondary electrons. A detector attracts these secondary electrons and quantifies them per point. When no secondary electrons are detected, a black pixel is seen on the computer screen. The more electrons that the detector detects, the lighter the pixel will appear. Once the raster scan is completed, we will now see a magnified image of the unknown sample. Amazed by the intricate morphology of the sample, you wanted to know what elements it was composed of. Let's add another component called the X-ray detector and zoom in on a single point on the sample. After a beam of incident electrons strikes this point, a low-energy electron in the sample's inner shell gets displaced, leaving a hole for the outer electrons to fill. But outer electrons tend to have higher energies than the inner holes require. To compensate for the energy difference between the two electron states, an X-ray is released. The detector quantifies the characteristic energy of the emitted X-ray that is unique to the element, and with the use of the software, the identity of the element is revealed. The spectra on the right shows the different elements that make up the sample. From the EDX spectra, you recall that your lab mate had been working on copper-based metal organic frameworks for catalysis. Judging from the morphology of the sample and the presence of copper and silver, you now think that the sample could be silver-doped HKUSD1.